Dear student, we are going to share with you how to write a closed loop on in a MATLAB using Simulink. Now we'll share with you the screen. Here it is the MATLAB. For Simulink, we have to open the Simulink library, as you can see at the middle, the top. I'm just waiting for the library to open. Takes a while. It is open, the library. Now for the before to start, of course, we have to open a new file. This is a file, a new model. So the screen on which we draw the Simulink loop will be shown. Here it is. As you understand from previous lectures on using MATLAB, we have to choose continuous. And imagine in the continuous system, we have to choose our system. Let us imagine we have a first order system. Here it is the transfer function. Now double click on the transfer function. Let us assume we have the gain equal 3 of the transfer function and the time constant equal 10. So this is 3 upon 10 as a plus 1. Apply. Okay. For the let me enlarge it a little bit. This is for the process in the closed loop. To construct the closed loop, we understand it has a load and a process. For the load, we can have another transfer function at the top. It is, we copy it, drag it, double click. Yes, we can assume it is 1 divided by 10 as a plus 1 as the load. So, okay. Now we can enlarge it a little bit. So these are the load and the process. For those, what else we need? We need the controller. We need the input. We need the output. This is the system we have. Then to construct the loop, we go for the common or we go for the mathematical operation. Here it is. We can see the mathematical operation, equation, mathematical operation, additional source. Either we go for the common. This common operator we have to use for the sum. For example, here, when we add the sum here, to add the input, and the gun again for the gain. Here it is the gain for the valve. Similarly, gain for the measurement. And for the measurement, we can, because you can see the direction here to the right, we can switch it to the left. We go to the rotating clip and we rotate anti-clockwise, or again, rotating anti-clockwise. Now it is changed to the left-hand side. And regarding, we need another sum to the set point part. Here it is. And then for the loop, you can see this is the gain. I can double click on the text. I can say valve. We can change. You can see the text. Even here, we can say it is a measurement, or gain 1, gain 2 is the same. Measurement. Now for the values, let us assume for the measurement we have 1. We open it, it is 1. So it's okay. For the valve, let us assume it is 1.5. Apply. It is okay. Now we have a valve, measurement, and the process. We connect the valve to the process. Now for here the load, so the load, it should be connected to here to the circle. And this circle now, it is, you can see the summation. We can enlarge it a little bit. This is, let me delete that, enlarge it, enlarge it. You can see the summation, one to the left, the other at the bottom. So we can change it to be one to the left and the other at the top. So double click. So here it is, instead here that vertical line deleted, and we put it at the back. Here it is, we put one at the back at the end of the plus sign. Okay, you can see it's been applied. So each time we do apply and okay, you can see that's the line. Here it is. Now they are connected. What else we need? Now we need the controller. We go back to the continuous, and then we choose the PID controller. Here it is, the PID controller. We dragged it, and in here, this is the summation. Here it is. It is a plus minus, as you understand. Double click, so it is now plus, and the one at the bottom becomes minus. We delete the plus, we add minus, apply, and so okay. You can see the negative part. It is now at the bottom. Enlarge it a little bit. You will see this is a negative, plus minus. Now we need to connect the measurement to that comparator, and here the summation, the output. This is the output, right? We need a line from the output to the measurement. So we take one to the measurement. Here it is now, it is connected. The output, we need to go to the real output. We go to the sink. The picture for the sink, we choose scoop. This is scoop in here. That's where we see our picture, and we connect the scoop to the process. And we may need a simulation or a data collector. Here it is, and we need now take data collector here. That's the output. So anytime we can get Excel or a data for that, for redrawing in Excel or in other software. Now for the controller, we connect it to the valve, and the comparator, we connect it to the controller. Left the inputs, it is, we go to the source. We could choose a step change. Here it is, a step change. We put a step change to the load, and we put a step change to the closed loop, and we connect those in here. You can see now closed loop connected. Now for the step change, we open it. The initial time should be 0, maybe unit step, or we put it equal to the step. Apply. It's okay. Again here, we can do it in a similar. In a similar, we put that 0. We can put that to a 2 as a set point, and apply. It's okay. You can see now it's constructed the closed. But before run it, we have to choose type of controller and where the changes. Is it in set point or in load? If it is in load, regulatory. If it is in set point, the servo. If we choose the servo system to change the change in set point, we have to disconnect the load because it cannot be run on two changes at the same time. So let us choose the servo loop. Now this is the controller. Double click on the controller. It's open. You can see proportional integral derivative. This is a PID controller. Now PI, proportional 1, and the integral 1. This is just a first start. It's okay. Everything now it looks fine, constructed. Let us run it. So now unit step, the step it is 2. Run. You can see way this is now operating. I press the green arrow. We have that voice sound. It means everything's okay. Now we'll click the untitle our program, and to click the scoop, double click on the scoop. You see the picture. Here it is our picture. You can see now this is the picture of the. Let me enlarge it a little bit. This is the response. It is oscillate because it is a PI. I may increase controller gain and see the effect. Double click on the controller. Here it is. Let me put the controller 2. Let us see the apply. That's the gain 2. The integral action left 1. Okay. And then to run, press the green button. until we hear the sound of completion. Now double click on the scoop. You can see now is getting an oscillation. And we'll continue that. Let me reduce the integral action. Double click on the controller. I can put the integral equal 0.5. It means faster to come to set point. Apply. Okay. Now to run, just click the green button until we hear the voice sound. And if that's run, double click on the, now this is the picture. You can see now this is the response. It's reaching 2. It's reaching 2. And let me again increase the controller gain. Let us see the effect to put the controller gain, maybe 5. Apply. Okay. Run. Let us close that. Double click and see this is the response. So by increasing the gain, the set point, it is changing up. And let us remove the, put the integral action. Sorry, that's the main. Put the integral action equal 2 or 3. Apply. You can see this is run. Double click on the scoop. You can see start to oscillate. Here the PI, actually the value of the PI, as you can see in the equation, it's written I1 of IS. This is the proportional, integral, and derivative. This is the derivative. So that's based on that particular. I may change now my controller to another set. You can see this is as a reset. They call it reset, the inverse of the integral action here replaced. The inverse of the integral action is replaced. You can see you reduce the integral action, it means faster. Dear student, uh, let us now try to change the controller parameters for this first order process. As we said earlier, that's when double click on PID controller. First is the controller gain, KC, and then the integral. But here, the integral, as you can see, it is from this equation on the right hand side, it's written P plus I. So I here is the inverse of I in the transfer function of the mathematical model of the controller. If you remember in the controller, the theoretical, it is Kc plus 1 upon Is, or as a integral 1 upon I integral 1 upon I integral dt, and so on. So here the value is the, what they call it, reset. So it is 1 upon the real I, 1 upon the real I. So here, if I put integral action equal 2, it means I in the real, it is 0.5. So it should be shorter. The value, it is opposite, is the inverse. So now you can see by increasing the I here, the integral, it means faster to reach. So it's the reality is the inverse. So here I is the inverse of the real integral action. This is the reset. Now we apply. Okay. So we can see just by click running. And then double click on the scoop. To see the response here to start oscillating. So here by increasing the I in the formula of PID here, it should be oscillate, but the real, it is the inverse. So now we are putting 2 is the inverse of the integral action, is the inverse of the integral action. We need the shorter integral action to reach the set point. So we here we have to put the inverse of I to get the real value of the integral, or the reset value. Now when increase the value of Kc, let us put that, keep it to 1, and increase Kc to 5. Let us see what happened, the response. So, okay, and then run. We have that sound. You can see now integral action 1, so that the response start no oscillation, because we are increasing the reset value. Now let us increase KC. Let us see what's happening. We put it 10. Apply. Okay. And run. Double click on the scoop. It is, you can see the starting to get faster to reach the set point. You can see this is reaching faster to change the set point. So here the player term is the integral action. Reducing the integral action, the system get faster, but at the same time get oscillate. But the normal process, if you remember, has no oscillation, but the integral action make it oscillate, and this is the response. Will never start oscillate, but because by increasing the integral action, the real integral action, reduce it, system start oscillate. And then, by the way, we can get an optimum response. For this system, just double clicking here to get the tuning. And then we can see here the word tuning. Tune. So pressing on the tune, you can see now started tuning. Started tuning. Takes some time. So it gives you the best controller settings for this particular process, which is first order system. Let us see. Now this is the picture. You can see now, we close this window. You can see this is the base response. This is the initial what we've got. And this is, you can see this is the tuned, and here it is the block. So this is our block, and this is the tuned. So they said this is the tuned. When we go like to see show the parameter, and here it is the parameter is shown. It said KC equal 0.29. They reduce KC. And here it is the value of I. It is in the block what we've got it before, 10 and 1. Here it is 0.2 and 0.04, but the inverse of 0.04 or 0.05 should be almost about 50. That's why it takes longer time to reach the steady state within 35 seconds. It depends on your time constant. You may say, I need this one, but their application will not be easy in control system, will not be easy. The controller will start rippling. So this is the best controller is given. You can see here start oscillate, because the value it is here, it is the gain, it is very, very small compared to the integral action. Here it is very, very small. So it means I around 1 upon it is 0.05, so equal around 20 something, around 20 something. Let us say the real value equal 1 divided by 0.05, which is, as I said, equal around 20, but the gain equal 0.5. Let us close this window, and now let us put the controller equal 0 and put the gain equal 1. Only controller gain, apply, only KC, and let us see the response. So now we are just playing with the parameter and see how they are. You can see now the response by only so there is a value. Here it is. There is a value, an offset. So you can see there is an offset, because now we are using just controller gain with 1. By increasing controller gain, offset will become smaller. Let me put it equal 10 as before, and integral action equals 0. Apply. Now run. You can see scoop. You can see by increasing the KC to 10, the offset being reduced, so almost reaching the step change in set point. Now this is response of first order system under PI controller. Now we may introduce a date time. So let us see what is happening if we introduce a date time to the system. So here it is. We move that a little bit here. We connect the controller again, and here it is the transport delay. We bring the transport delay here, drag it, double click. So the time delay equal 1. Let me put it 0.5. And we don't play even the initial buffer is the number of data we are storing. So it is acceptable. Okay. Now we connect those two. We connect the process to the delay, and then delay to the comparator. We have a delay. So the same, the controller. You can see now the controller, it is only, let us come back, put it equal 1, and the integral action equal 1. Apply. Okay, we had similar response before. And then run. Let us see the effect of date time on the response. Double click on the system. You can see start oscillation. Before, without date time, wasn't oscillate. The system wasn't oscillate. You can see now start oscillate. Start oscillate. By increasing Kc or decreasing I, but here in the equation we have decreasing I, it means faster, it means more oscillation, but when we apply it in the controller, we have to put it opposite. So we may put the value of, put it here 2, it means 0.5 in the real equation. Apply. Okay. Now to run. Double click on scoop. You can see start oscillate. You can see more oscillation. More oscillation. Now this can be utilized to find the optimum. Again, I can read. You can see now. Let us see the optimum. Tune. This is the optimum setting. Now in launching the PI, because not the derivative equals 0 here. Launching. You can see now it's working. This is the best system. You can see this said this is our block, and here it is the base settings. Let us see what the value he gave. So for the controller, here it is. You can see it was 1, and again the integral it is 0.5. So we put it 2 in this Simulink. You can see here the value it is requested to be 0.05. Again the same, which is around the 20 integral action, and the Kc equal 0.3 to give me this is a smooth and nice oscillation, smooth nice response. Sorry. The big oscillation that it was for our previous setting when Kc equal 1, and we put integral action for this equation 2, but in the real one it should be the inverse. Now this is, I can close it. Now I can use this Simulink to find the free oscillation response to apply Ziegler-Nichols. In this case, I put the integral action 0, and then we start increase Kc to reach the oscillation. Now let us apply 1, so there is no integral action. Let us see how the response will be. You can see now there is no oscillation, but there is a delay. You can see the response delay. Now let us increase Kc, double the Kc. We put it equal to, apply. Okay, and then run. You can see start little bit oscillation. Again, let me increase Kc, put it 6, apply. Okay, and then let us see scoop, start oscillate. So I keep increasing Kc until reach free oscillation. Maybe put it equal 8, because we have to increase by 2. Okay, run. You can see now this is free oscillation response. Still, this is less oscillate, but now we reduce. We have to reduce Kc to 9, to 7. Let us see. This is 7. Apply. Okay, now run. You can see here the scoop. Here, this is again. You can see now the oscillation between 7 and 8, but it is 8. It is the best response. It can be used for Let me use 7.5. Let us see what type of response we will have. Apply. Okay. And then this is the run. You can see now it is start oscillate. So we choose 8, as we said it earlier. It was free oscillation, and it can be used for Ziegler-Nichols method. But if you wish now to go for the tune, this is the best tuning for only proportional controller.